Very good morning to all of you. For good ideas and true innovation, you need human interaction, conflict, argument, and debate. With this goal, I would like to start my welcome speech on behalf of EPCET and the Department of Electronics and Communication Engineering. Myself, Dr. Chandrapati D.L., Associate Professor. It gives me a great pleasure to welcome all of you for the second day sessions of National Conference on Next Generation Intelligence in Electronics and Communication Engineering, NGIEC 2021. First and foremost, I would like to extend my sincere gratitude to Founder Chairman of EPCET, Dr. S.N. Venkatapati. I wish to extend my hearty welcome to Honorable Chairperson Srimati P.L. Ramadevi Venkatapati and the young and energetic CEOs of EPCET, Sri S.V. Pramod Gowda sir and Sri S.V. Rajiv Gowda sir in their absentia. I am profoundly delighted to take this opportunity to welcome and introduce keynote speaker of the day, that is Dr. Muralidhar Kulkarni sir. Professor Muralidhar sir has received his BE degree in Electronics and Communication Engineering from UEC Bangalore and a master's degree in Satellite Communication and Remote Sensing from Indian Institute of Technology, Kharagpur, and a PhD degree in Electronics and Communication Engineering from JMI Central University, New Delhi. He worked as a scientist at Central Power Research Institute, Bangalore, and as an aeronautical engineer at HAL Bangalore. He served as an assistant professor in Department of Electronics and Communication Engineering, UEC Bangalore, and as associate professor in Department of ECE, Delhi Technological University, New Delhi. He joined the Department of ECE NIT Surathkal as a faculty in 2008. Currently, he is working as a professor in the Department of Electronics and Communication Engineering in NGIEC. He served as a HOD of ECE and also chairman of ECE and the Career Development Center and member board of governors. And currently, he is the coordinator for Center of Excellence in Wireless Sensor Networks at the NIDK. The current research interest includes digital communication and networking, that is the YFDM, WSN, SDN, congestion control, 5G networks, and IoT. And also optical communication and networking, that is the free space optical communication, microwave and antenna systems. Dr. Kulkarni sir is a senior member of IEEE, fellow of IETE, life member in ISTE and CSI. He has published more than 80 research papers in international and national journals and conferences, and also has credited several funded research projects and delivered a keynote address in technical talks and also national conference in workshops also. He has also authored and co-authored for 5 very popular textbooks in the area of microwave radar, DSP, information theory and coding, analog and digital communication. Such an eminent personality with us today. Sir, very warm welcome to you, sir.
Thank you very much.
It's my pleasure to welcome our beloved principal, sir, Dr. Prakash, sir. Welcome you, sir, for this second day session. It's my pleasure to welcome our beloved HOD, sir, Dr. Yogesh, sir, for his constant support. Welcome you, sir. I request Dr. Rajesh L. to present a packet as a token of respect. I wish to extend my warm welcome to conference coordinators, Dr. Jayanti Kumari, Professor, Department of ENCE, and Dr. Sachin Sharma, Professor, Department of ENCE. I request Dr. Hemodi Madam to present a working. I request Dr. Pasha sir to present a working to Dr. Sharma sir. It's my privilege to welcome all faculty members of UNC department for this conference. Welcome you all. I would also extend my warm welcome to all session chairs. And also, I extend my warm welcome to the faculty members of other departments of EPCET. I am delighted to welcome all students participants for this conference for the second day. And also, I extend my warm welcome to Dr. Anandji Madam. I request Vasu Madam to present a poetry. Once again, warm welcome to all. Thank you. I would like to call upon our beloved HOD sir to speak about this conference. So, over to you.
A very good morning, everyone. Respected leaders and the dais, respected HODs of all the departments, respected faculty members, and my dear student friends, and the participants of the national conference. It's a great pleasure and honor to speak on this occasion. We have come to the second day of the conference. The first day sessions went very well. For the second day, I heartily welcome all the paper presenters of the day, and I wish them a very good luck. Kulkarni sir, I heartily welcome you on this occasion. Thank you very much for your kind time. With these few words, I'd like to welcome all of you, and thank you very much. At the outset, I also welcome Dr. Chandra sir. I would request Rajesh K to give a bouquet to Chandra sir. And for your time once again, I wish you all the best for the participants. Thank you.
Thank you, sir. Dr. Kulkarni sir, please take over the stage.
Yeah, thank you. A very good morning to each one of you. I'll just share my screen.
Sir, your screen is visible. Thank you, sir.
It's visible, no? Is it full screen?
Yes. It is full screen, sir.
Okay. So today, I'll be talking about time-sensitive networking, which has really become very important, particularly for real-time applications, particularly in the industry environments where real-time real-time devices are connected, something like in a 5G network and all. Definitely, we would require networks which are very time sensitive to time. That's why they're called time sensitive networking. I'll be going through. Are you able to see the next slide? I have some issue with sharing the slides. Let me check once again. Hello. Hello. Mobile to marle. ತಗೊಂಬ ಇಲ್ಲಿ ಸ್ವಲ್ಪ ನೋಡೋಣ. Hello. Hello. Hello, are you able to hear? I'm sorry. Hello, are you able to hear, each one of you? Hello, a very good morning. There was some problem in sharing of the slides. So the outline of my lecture would be, I'll just give a brief introduction to time-sensitive networks, and then I'll tell what is TSN all about. Then I'll talk about TSN components and where these things came from, and why TSN, what are the target applications for TSNs. We'll also talk about some benefits or existing methods, and which are the organizations which drive this TSN systems, who are the key enablers, and how is it different from IEEE 1588, which you are all very well aware. We'll look at some TSN verticals, then configurations, and which are the various standards particularly used for industrial automation, and then I conclude. Okay, so starting with introduction to TSNs. Okay, we all know that Ethernet is a layer 2 technology in ISO OSI reference models. Okay, the function of Ethernet layer mainly is framing, forwarding, flow control, error control, and multiple access. And Ethernet standard, okay, Ethernet standard, which is basically a wired standard, was basically defined by IEEE way back in 1983, and this standard is known as the IEEE 802.3, and all of us know about 802.3. It's a working group defining the physical and MAC layer of Ethernet, which also supports 802.1 architecture. Whereas 802.1 working group of IEEE 802 project dealt with the standards of LAN and WAN and their internetworking, network management and link security. Okay, it also defined various standards like 802.1M. Okay, it also defined the standards like 802.1Q, etc. We all know that 802.1Q is a standard that supports virtual LANs on standard Ethernet, that is the 802.3. So the initial speed that first standardized Ethernet could have reached was something like 20 Mbps, and the speed of around 400 Gbps was reached by Ethernet technologies somewhere in the year 2017. And IEEE 802.3, as I told you, is a working group of IEEE 802 project, And all standards defined within this project are dealing with LANs and MANs, metropolitan area networks. And time-sensitive networking, belongs to this 802.1 group itself. So the standard Ethernet technologies are very popular due to a high bandwidth, scalability, and compatibility, but they fail in providing, bounded data delivery for time-critical network. Hence, TSN was introduced to overcome, the drawback experienced by the standard Ethernet. In fact, an industrial automation network which deals with the critical and non-critical data transmission was required, and hence there is a need for efficient communication standards that converges both time critical and non-time critical data. As the slide says here, TSN is basically an enhancement to IEEE 802 networks, which enables the convergence of real-time control with time critical streaming and bulk data, okay, which is basically put into bulk data will be put into a single communication network. Okay, so it provides a guaranteed latency and low jitter and zero congestion loss for all critical control data of various data rates. It also reduces the complexity and cost through convergence of multiple kind of applications into a single network. It protects critical traffic to effects of converged and non-critical bulk data traffic. So it also simplifies overall networking through common design, provisioning, and maintenance of a single infrastructure. So what I mean to say is TSN is basically a set of standards which is still under development by the time-sensitive networking task group of the IEEE 802.1 working group. And this TSN task group, was formed in November 2012 by renaming, the existing AVB, that is Audio Video Bridging Task Group, which is actually still continuing its work. The name changed, as a result of the extension of the working area of the standardization group. In fact, the standards define mechanisms for time-sensitive transmission of data over deterministic Ethernet networks. So the majority of the projects, define extensions to this IEEE 802.1Q, that is basically bridges and bridge networks, which describes, virtual LANs and network switches. So these extensions in particular address the transmission of very low transmission latency and very high availability. In fact, the applications include the converged networks with real-time audio-video streaming and real-time control systems, which are used in automotive or industrial control facilities. Okay, so going to the next slide, we can see, we have various types of traffic types. We have what are called as best effort traffic, which is basically a low priority traffic without timing and delivery guarantees. That is called the best effort traffic. Then we have what is called as rate constrained traffic, RC traffic. Each flow will have a bandwidth limit, defined by two parameters. Okay, the minimum inter-frame intervals and the maximal frame size. That is called the RC traffic. And the third type is the time trigger traffic. Each flow has an accurate time to be sent. In fact, this belongs to the time sensitive network traffic, high priority traffic. Okay. So for real time and time critical traffic, the data must be delivered. Okay, there are two aspects. The data must be delivered within a certain window, typically before a specified maximum delay. So latency becomes very, very important for TSN real time and time critical traffic. And the connected devices need to have a common sense of walk clock time for synchronization, coordination, and phase locking, etc. In fact, both of these aspects are actually mandated for time-sensitive networks, that is TSNs. Okay, so the main goal of TSNs is basically to provide deterministic services over IEEE 802.3 Ethernet wired networks. So we are looking at the layer 2 of the OSI model, which you all of us know. So it is actually same as normal networking, but with the following features for critical data streams. The most important is the time synchronization for all the network nodes and the hosts should be better than 1 microsecond, as small as 1 microsecond. And the software for resource reservation
for critical data streams, that is the buffers and schedulers in the network nodes, and bandwidth availability on the various links via configuration, management, and/or protocol action. That means the TSN networks should have sufficient buffering capability. They should have proper scheduling mechanisms and allocation of bandwidth for different types of traffics which we have just now discussed. And even the configuration should be different for TSN networks, and they have to be managed in a totally different way compared to the normal networks. And even the protocol action probably needs to be changed. Okay, so the software and hardware to ensure extraordinarily low packet loss ratios, starting at something like 10 power minus 6 and extending to 10 power minus 10 or better, and as a consequence, a guaranteed end-to-end latency for a reserved flow is what is the requirement. So the convergence of critical data streams and other QoS features, including ordinary best effort on a single network, even when critical data streams are 75% of the bandwidth. So this is where the convergence of internet traffic and the critical traffic has to be taken care. Okay, actually, who needs this kind of deterministic networks? That is a question which anybody will ask. So there are two classes of bleeding edge customers. Okay, one is audio video. All of us are mostly audio video, but there is a big industrial sector. Okay, they are bleeding edge customers, as we call them. So we cannot leave this industrial customers. Audio video anyway we have been taking care of. So we need to take care of industrial automation as well. And the present day is AI and ML related industrial needs, real-time industrial needs. So the both of them have moved into a digital world, and some are using packets, but now all of them realize that they must move to Ethernet. Okay, and most will move to the internet protocols. That means at layer 2 itself, we should be able to have the internet protocols kind of stuff which has to be put in layer 2 as well as in layer 3. Okay, so we have two bleeding edge customers, as I told you, industrial, which is required for process control, mission control, and even for vehicles. In fact, autonomous vehicles like robots managing the entire industrial real-time needs. Okay, so at layer 2, this becomes the IEEE 802.1, which is nothing but the time-sensitive networking. This is normally not taught in BTech levels. Even MTech, I don't see anybody has included time-sensitive networks as a part of the syllabus. Okay, so that is where I thought time sensitive networking should be dealt in such a conference, which will tell us that there are some industrial requirements in addition to the audio video customers like us. So the audio video streams in live production studios, as we are doing right now. Okay, again this should be done at layer 2. That becomes 802.1. This is the earlier one, audio video bridging mechanism, AVB. So not so many flows, but one flow could be as high as 3 gigabits right away, and tomorrow it could be as high as 12 Gbps or even higher. And latency and jitter definitely are important in audio video streaming as well. And buffers are scarce at these particular speeds, but industrial needs take higher preference, although audio video customers are even more important in present day circumstances. But we can't forget the industrial, they are called bleeding edge customers. Okay, so coming to what is TSN. Okay, so TSN is all about layer 2 of the OSI model. Okay, and an extension to the IEEE 802.1 to make Ethernet a deterministic network, which we just now discussed. It should be more robust and highly reliable. So we are showing TSN in the data link layer of the OSI model. Okay, so all data frames in TSN will be a layer 2 protocol. So the features will be targeted at industrial, even automotive applications. Okay, of late self-driven automotive cars have become very, very important. Okay, so features generally are targeted towards industrial real-time applications, automotive applications, and of course audio video bridging as well. Okay, first and foremost TSN adds time to internet, to the standard Ethernet. Earlier, Ethernet really didn't bother much about time. It was not so much sensitive to time. Okay, so the common understanding of time and clocks becomes very important in TSN. Okay, so TSN uses time to ensure predictable message delivery. Okay, in terms of shaping the data traffic, in terms of bandwidth, or multiplexing and multiple access technologies which will be required to do this traffic shaping. So TSN basically uses time. That's why it is time sensitive networking. So it also adds robustness and reliability with the seamless redundancy, and we can actually preempt what is going to happen. Okay, and we have to preempt and then take decisions, particularly in real-time situations. Okay, so continuing with what is TSN, as I told you, it is an extension to standard Ethernet, and it's a set of standards maintained by IEEE 802.1 task group. Okay, it is in layer 2, and the goal of TSN is to provide bounded latency. That means there is a latency requirement and extremely low data loss. Okay, we cannot lose data here, and for time critical applications. So we have different types as pipes here. You can see here. Okay, broadcast video, precision time synchronization, real-time control for safety applications, particularly when you're having a auto-driven cars, no driver required. So real-time control may be required, real-time actions are required. So network also need to be controlled in a different way, and IP telephony is already in existence, and high throughput data also may be a requirement. So this is a bigger pipe involving all these services, okay, time critical as well as internet requirements. So I can just talk about the most important TSN components, time sensitive networking components, okay, which will require synchronization requirements, latency requirements. Okay, it must have proper resource management requirement, and hence highest reliability. So as I told you, time synchronization is very, very important. Timing is the major requirement of TSN networks. Bounded low latency. Okay, so credit based shaper, frame preemption. Which frame is important? We have to assign priorities to various kinds of frames. Okay, and schedule the traffic properly. So you should have scheduling becomes very, very important here. So scheduling the traffic, frame preemption, and credit based shaper, okay, is very, very important. We may require some kind of cyclic queuing and forwarding technique, and definitely it should be asynchronous in nature. So asynchronous traffic shaping may be the requirement. Okay. When we come to resource management, we should have dedicated resources and APIs, particularly for TSN networks. So we may have to use some kind of stream reservation protocols. So a lot of research components are there in TSN networks. So one is, okay, to have different shapers, preemption techniques, frame preemption techniques. There is a research possibility. Scheduling of TSN traffic could be another research area. Various queuing models which have to be necessarily queuing. Different forwarding techniques can be thought of. We should also look at asynchronous traffic shaping techniques, and also various reservation protocols. Okay, the present day protocols may not be good enough because they have to be time sensitive. So I must have a proper configuration, and we may have to have a different configuration like link local reservation protocol also could be a requirement. As I told you, reliability is very, very important. Okay, so we must have ultra reliability. Frame replication and elimination, okay, should be done within a specified time period, and path control also should be under control. Which path to take and how fast you can change the path which you have to take to send time critical information. So per streaming, filtering, and policing also may be required. Okay, time sync reliability. So all these things require a high amount of reliability. Okay, so TSN components basically will involve synchronization components. Reliability is an issue of all those components. Latency is the biggest requirement. Should have bounded low latency. Should have dedicated resources, and APIs will be required to maintain to manage the entire network. Okay, so where did this TSN come from? till recently, this was not being talked of at all. It's only after 2017 TSNs have come into picture. Even in industries, people are not aware of TSNs. I don't see much research. Very few papers have come in this area. I have given a big list of references at the end of this lecture. So bridging was originally defined by 802.1b. When virtual LANs, VLANs were added to this specification, it became 802.1q. So basically, I'm talking about standards here, how we must move from the AVB standards to TSN standards. However, this didn't address the determinism and robustness requirements for industries like factory automation. This is the most important thing. Why Chinese and Japanese have become number one is because they have started working on time-sensitive networks much before than other countries. Okay, so starting in 1999, various industry organizations were formed to address these requirements, like various people, like PNO, ODVA, ETC, etc., developed their own non-standard. Read the word here, non-standard deterministic Ethernet variants. They have not become a standard even today. So TSN standards are yet evolving. We need to have a TSN Ethernet standard, which will be done in a very maybe in the next few years we will see that. So in 2006, IEEE began to address this determinism with the formation of initially audio video bridging AVB group. That was in 2006, and in 2012 the charter of the AVB task group was expanded for a wider range of deterministic Ethernet requirements. Okay, so before 2012, this was not thought of at all. Okay, so this is the 802.1 task group, which we now call as the time-sensitive networking group. Okay, so the foundation for TSN is basically the AVB, which had a protocol called the Generalized Precision Time Protocol, GPTP as it is called. It was called as 802.1 AS, which was developed in 2011. It's a layer 2 profile of the IEEE 1588 Precision Time Control Protocol. I was talking about IEEE 1588. It's nothing but PTP protocol, Precision Time Control Protocol. So it started in somewhere in 2011, 2012. Okay, so immediately after that, we had 802.1 QAV, okay, which dealt with forwarding and queuing of time-sensitive streams, FQTSS as they are called, forwarding and queuing of time-sensitive streams, which actually specifies a credit-based shaper system. Okay, traffic shaping I'm talking of. Okay, like credit-based grade system we have in academia today. We also have what is called as credit-based shaper in time-sensitive networks. Okay, so after that, they developed what is called as 802.1 QAT, which actually involved the Stream Reservation Protocol, SRP. It's very widely known. Registration and reservation of time-sensitive streams. Okay, how to reserve the resources for time-critical streams which have to be transmitted in a network, along with other non-time critical streams as well. So then they started off with 802.1 BA, which are basically AVB streams. So overall AVB architecture and AVB profile actually became the foundation for the time-sensitive networks. So why to go for TSN? I have just told you already. It's basically convergence of IT with OT. So all of us, we're actually talking of only IT, information technology. We need to do what is called as convergence of IT with OT, which is basically operation technology. So we have some real-time critical applications which are there in the field level and the control level. And there are some non-critical applications like your IT. IT is non-critical, whereas OT is critical, real-time critical operation technology. So it requires a deterministic data delivery and improved quality of service as compared to IT. So process control level and enterprise level. So IT will involve the enterprise level and the process control level. They are non-critical applications, not very important. When you come to control level and field level, the industry, where real-time operations happen, we have what is called as operational technology. So real-time critical data streams are in the bottom operation technology levels, whereas non-critical applications like your ERP solutions, the internet service providers, all of them operate at the enterprise level and at the most, process control level, not, at the control level and the field level. So real-time critical data streams would actually require a time-sensitive network. Okay, so we need to have an open standard. Okay, and which we also should reduce the complexity between multiple buses, which are operating. Okay, how to integrate, IT and OT is a big challenge. So convergence of IT and OT becomes a very important requirement for the future researchers and standard making bodies. Okay, so why is TSN important? Okay, I told you it provides a common layer 2 for all upper layer protocols. Okay, so that is, the 802.1 TSN and related foundational services. Okay, which basically involve time synchronization, quality of service, redundancy, security, network configuration, etc. Okay, it will provide a common layer above all upper layer protocols, including layer 3, layer 4, etc. So it becomes, okay, the future industrial protocol. So TSN protocol is going to be the next generation. That's why I thought of doing, TSN, because this conference is all about next generation. Okay, so next generation industrial protocol is going to be the TSN protocol. The current Ethernet standards may not be good enough, okay, for operational technologies, which are very, very important, particularly in the manufacturing sector. So the benefits, of TSN over existing methods are, okay, it is an open standard through IEEE 802. I told you about the convergence of IT and OT. The improved asset utilization will happen. Reduced implementation costs, because I try to take care of low latency and high reliability. So the implementation costs will certainly be reduced, and it results in a reduced development life cycle, increased flexibility, and enhanced security as well, because you are working at the bottom layer of the Ethernet. Okay, there will be enhanced security as well, because you are not in the IT layer at all. Okay, so the target applications for TSN would be something like this. They can be, simple distributed synchronized measurements. Okay, particularly, the electrical people, okay, generally talk of synchronization in a big way. Okay, how to synchronize the grids, okay, becomes a major problem. So same thing is required in a networking environment as well. Okay, so they too have different IEEE standards for synchronization purpose. Even we need to have, okay, these distributed synchronized measurements, which can be done by using a TSN. So we require, embedded, coordinated, distributed data logging requirement. So advancements in next generation, okay, computer numeric control machining could be required. This is the target application. Okay, so novel semiconductor processing machines. You want to make an IC. Okay, the machines which are involved, okay, in making chips, even they may require, time sensitive networks. They can't afford, they should be, very, very time critical. So even the semiconductor industry, okay, will require a TSN network. So future electrical grid research, I was talking about, electrical systems where they use a lot of synchronization techniques. The future electrical grid research, okay, that will be the next generation research, which will definitely involve, TSN. Okay, so we need to have, test cells and distributed monitoring. So mission control, hardware in the loop, they are called HIL systems. Automotive networks, I was talking of, self-driven cars, okay, automated cars, auto driving, etc. So media networking, all of these are basically, the target applications for TSN. Very, very important area to work on. This is the real next generation standard. Okay, TSN standard, time sensitive standard. So how is it different, from IEEE 1588? We have already told about this. So IEEE 1588, was focusing on time synchronization only, whereas, TSN will add several other features which will be added to the Ethernet 802.3. Okay, so mechanisms for time synchronization is given by what is called as 802.1 AS. This is already being used. Then we have mechanisms for using coordinated time to schedule the traffic. So that is called a QBU protocol. Okay, how to have excellent mechanisms to coordinate, these scheduled traffics in a particular time slot. So time slotting and scheduling the traffic becomes very, very, very important. And this was actually provided by a standard 802.1 QBV standard. So these are, natural standards which have already come into picture. So 802.1 AS is already proved and published. 802.1 QBV is basically for coordinating time to schedule the traffic. And then we have 802.1 QCC, which is basically to assure, simple and scalable system configuration. So TSN configurations can be managed by using this 802.1 QCC standard. So every major industrial vendor is actually contributing and planning for options as to how to utilize this TSN. Okay, that means a lot of industries are putting money into this very important area of time-sensitive networking. So every major industrial vendor is contributing and planning for options on how to utilize TSN. So this is the real next generation thing which is going to happen. That's why, my latest PhD student has been asked to work on TSN. We already published a conference paper on time-sensitive networks. We have done some simulation studies, and in an international conference, we have trying to publish. So which are the organizations which are driving a TSN? Okay, so if I look at the organizations which are driving TSN, you can see the organization here. Initially, IEEE, which started developing standards and recommended practices in the areas of 802 LAN-MAN architecture, that is local area networks and metropolitan area networks, internetworking, security, and overall network management. In fact, IEEE is being funded by NI, Siemens, Rockwell Automation, and GE. So these are the major industry people, which all of us know. National Instruments, Siemens, Rockwell Automation, and General Electric, GE. Okay, so then there is an organization called AVNU, which is a community for creating an operable ecosystem servicing the precise timing and low latency requirements of diverse applications using open standards through certification. So a new organizations, in addition to IEEE, was formed as a community, to have this TSN standards coming up, which is actually required by all these industries. You see the people, who are working. So each of these people have already got TSN components. They are making components, which will be compatible with, TSN networks like National Instruments, Rockwell, Bosch, Rexroth, GE, Mitsubishi, Schneider Electric. So all these companies are basically, if you say TSN, your job is assured in the market today, because they don't have people who know about the TSN. So there is now an industrial consortium, which will take care of IT and OT requirements to bring together all the organizations and technologies necessary to accelerate the growth of the industrial internet. So TSN is setting a path towards what is called as industrial internet. We have the present internet used for audio and video streaming, because the industry requires this industrial internet, which is driven by TSN. So you can see NI, Bosch, Schneider, B&R also being involved here. So these are the organizations which are driving TSN, and maybe in the next 5 years there will be a lot of job requirements in these areas. So if you look at the TSN verticals, for industrial automation, in fact, even in 5G, TSN is being talked about. 5th generation networks, which are basically, trying to reduce the latency. It will be a distributed kind of 5G network, and the people are trying to use TSN standards for 5G applications as well. I could find some information. I had those slides, but I removed them due to paucity of time. Otherwise, I wanted to talk about how TSN can be as well used, particularly for ENC students in 5G standards. So in 5G networks, how to integrate 5G networks with the TSN could be a fantastic next generation network. So IEEE and IEC, that is the International Electrotechnical Commission, that is IEC standards, all of us know, are together developing the so-called dual logo standard to define TSN profiles for industrial automation. Okay, this is very, very important. Industrial automation. Okay, so IEC and IEEE 60802 is a requirement which is used for industrial automation. So the potential TSN components and corresponding 802.1 standards for industrial automation basically includes TSN, okay, synchronization requirements, reliability requirements, low latency requirements, and resource management, which I have already showed you in earlier slides. Okay, so the potential TSN components and the corresponding 802.1 standards have to be merged, okay, have to be converged, okay, to make all these applications possible. Okay, so I am just showing the same slide once again, how these 4 TSN components become very important: the synchronization, the reliability, the latency, and the TSN, the resources of the network, which has to be extremely low loss, bounded low latency, and low delay variation. So these are the 3 very important requirements. Okay, extremely low loss, guaranteed data transport. So these are the reliability requirements. Okay, guaranteed data transport, extremely low loss, bounded low latency, and low delay variation. So these are the requirements of TSN networks. So the key enablers of TSN, as I told you, in time synchronization, we need to extend the PTP protocol, particularly known as the GPTP, as far as 802.1 AS protocols are concerned. And then we have the scheduling, which is basically the time-aware shaper, okay, which I told you it is basically 802.1 QBV. If you are using preemption, that becomes QBU, okay. And for network configuration, the network should be configured automatically, okay. So timing synchronization, scheduling, okay, network configuration, and reliability become very, very important. So in reliability, the frame replication becomes important. We may be able to eliminate, etc., etc. So all service requirements are very, very required. So these are the 4 important key enablers for TSN networks. Okay. So if you look at various TSN configurations, there are various configurations. We can use what is called as a fully centralized TSN configuration. The model is shown here. Okay, so many TSNs have different use cases, and each of those use cases may require a different user configuration, okay, in the end stations, okay, which can act as listeners and talkers. So we have talkers and listeners in a network. Okay, we'll have several bridges in between, and how the information flows from the talkers to the listeners either way, and how they have to be managed. Okay, so that can be centralizedly controlled. That's why it is called a fully centralized TSN configuration, centralized network configuration. Okay, so there can be a user network configuration information. So you have user configurations, which is also centralized, a network configuration, which is also centralized. So the fully centralized model enables a central user configuration, which you call it as a CUC, okay, a CUC entity to discover end stations, which are the end stations connected to this network, retrieve the end stations capabilities and user requirements, and then configure the TSN features which are required by these end stations. Okay, so all user requirements are exchanged between the CNC and CUC. So this is the CNC, this is the CUC. Okay, so locating the TSN UNI between the CNC and CUC. Okay, so how to have time sensitive or critical data transfer between the talkers and listeners in addition to non-critical information can be centrally controlled, or centralized control is possible by using CUC and CNC. Okay, so this is the fully centralized TSN configuration model. Okay, so I can also have what is called as a fully distributed configuration model, in which you can have end stations, that is talkers and listeners, communicate the user requirements directly over the TSN user or the network protocol. Okay, instead of going to a centralized model, I can have some kind of a distributed model, which is fully distributed now. The network will be configured in a fully distributed manner without a centralized network configuration, which you saw in the earlier slide. Okay, so the TSN user network configuration information will be propagated along the active topology for the stream. That means, the bridges in the tree from talker to listeners, okay, the information will propagate. That means the user network information, configuration information will be available with each of these bridges. So it's an active bridge, these are active topology, okay, which will have information or the configuration information between both of the user as well as the network will be available, okay, as an active model. Okay, so the bridge resources are effectively managed locally without the knowledge of the entire network. So this is another model. Sometimes, centralized model becomes more easier to control, like in case of SDNs, software defined networks. Some people in a particular real-time environment, okay, it is quite likely that we may use a fully distributed model as well. It depends upon the kind of application for which you want to use your TSN network. Okay, so I can have a fully centralized TSN configuration model, or I can have a fully distributed TSN model as well. Okay, or the best is to have a combination of both. Is it not? This is the ideal thing. I have a centralized network configuration. At the same time, the information of the user network configuration can be, there are some, TSN use cases that can benefit from a complete knowledge of, all streams in the network. That means a centralized entity can gather information about the entire network in order to find the best configuration possible. So it's almost similar to the fully distributed model. The end stations actually communicate, the talker listener requirements directly over the TSN UNI. However, the configuration information is directed to and from a centralized network configuration entity. All configuration of bridges for TSN streams is performed by this CNC. That means, there is a centralized control about all these bridges, which have user network information, okay, what the listeners and talkers want, okay, and what is the requirement will be, the information will be shared with the centralized network configuration or the CNC. So the edge bridges are configured as proxy, transferring talker listener information directly between the edge bridge and the CNC rather than propagate the information to the interior of the network. So thereby, there will be some kind of, the best possibility, you use the best advantage of both centralized as well as distributed user models. I think, this is what most people would love to have. Okay, so the entire company could have a centralized network configuration, and the actual, the bottom layers could actually use a distributed user network configuration. In fact, there are several list of standards. Okay, in fact, the whole of TSN basically involves, the various standards which have to be understood completely. As you can see, these are the various standards, several of them. There's a list of standards. So for scheduling, these are the standards. For reliability, these are the standards. When I say it is actually published, when I say it is T, it is still in the ballot. People are trying to vote whether, this 802.1 QCR, that is the asynchronous traffic shaping, it is still, being under ballot, whether it can become a standard or not. But these three have become, okay, the scheduling has been confirmed as a standard already. Then you have time synchronization. One of them is published, other one is, is a sponsored ballot. So various organizations, standard organizations, will have to test, the algorithm, okay, for its efficiency, and only then it can become a standard. So these are the time synchronization standards. And for network mechanisms, we have so many standards. All these are for network management. Okay, so many of them are already approved, and some of them are still, being balloted. Okay, TSN TC ballot as they're called. So this is the industry profile. Okay, the details. So building blocks for different standards for different use cases are being tried out. This I've taken from the website Automata, In fact, automation industry requires a TSN more than anybody else. And today industry is going towards automation. Okay, so that is why TSN becomes very, very important. In fact, I wanted to talk about at least the scheduling mechanisms and the synchronization standards. In fact, I wanted to go through 802.1 AS, QBV, QBU, QCH, okay, standards in this lecture. Because of paucity of time, I removed those slides. Otherwise, I had full details about how scheduling of traffic is done, how preemption of frames is being done in this standard, how cyclic queuing and forwarding technique can be used, how can we think of an asynchronous traffic shaping, and also how to make time synchronization, okay, by using already existing 802.1 AS, which is published, okay, and how to improve the standard. Okay, I had details about these 4 or 5 protocols. I removed those slides because I was given only 1 hour time, and we lost some 10-15 minutes, okay, in introduction itself. That's why I removed those slides. Okay, so these are very, very important. These are very, very important. In case anybody wants to work on TSN, they need to go through these standards. Only then they come to know how they can proceed. Okay, very, very important for automation industry. So the TSN related specifications and projects, as I told you, there's a set of 802.1 substandards addressing different needs. Not all substandard have to be implemented. So there are some important substandards for industrial automation, as I was telling you. Okay, I wanted to discuss these 5-6 protocols: time synchronization, time hour, traffic shaper and enhancement, ingress policing, ingress and egress policing, seamless redundancy, network management, and frame preemption. I wanted to discuss these 3, but it's not possible for today's keynote address. I think whoever are interested, they can go through the references which I have given. So there are other things which are still coming up. Okay, you can go through this slide. So these are the ones which are very, very important. So TSN and its future in industrial automation depends upon this UNO community industrial segment. Okay, which are trying to make the theory of all the operations have to be completely understood. Only then a standard can come up. So the goal is to certify devices in a few years from now, probably in 2023. Okay, you will have AV and NEO and IEEE working together. So then IIC TSN test beds are being done. So network operational with initial set of vendors. Even AMD is working for making ICs. Okay, SOCs. Okay, all many big players are there. Intel, AMD. Okay, GE. So several people, Schneider, okay, GE, okay, NI, they're all working on TSN test beds now. So goal is to expand the use of TSN as the use of TSN grows and explore the technologies. So there are several standard bodies. I told you how to integrate TSN into the specification. In fact, IEEE is in the process to finalize the remaining TSN sub standards, which I told you, a big list I had shown you. So TSN is an opportunity to converge on a common layer 2 technology for all industrial Ethernet protocol. This is important. So we have Internet Ethernet protocol for audio video streaming and for all other normal computer internet protocols. For industrial, we need to develop these industrial Ethernet protocol, which is basically a TSN protocol. So it has the power to provide interoperability at layer 2 in order to achieve a true converged network. So this is the goal. Okay, so TSN can be adopted by existing industry standards like Profinet or Ethernet IP to gain better and broader hardware support and converged real-time model at layer 2. In fact, a path to gigabit Ethernet. Okay, so I had some slides on 5G, how TSN can be integrated with 5G. I removed them because of paucity of time. It's already 11 o'clock. I think I'll end my lecture with these TSN and its future, which is required for industrial automation, which is the future. Okay, so I have several references, something like 15-16 references which I have. Okay, in fact 19 of them. I told you, these are the internet links which you can go through. Avenue, okay, IEEE, IA consortium, and time sensitive networks. There is a IAC consortium as well. So these 3 will give you a lot of information. Okay, and of course there are 15 publications, okay, mostly by industry people. Academicians, very few people are working in time sensitive networks. I think we should get into time sensitive networks. So with this, I end my lecture, and if you have any questions, I am open to them. Thank you for your patience. I am open to any questions.
Thank you, Kulkarni sir. It was a very wonderful session.
Yeah, thank you. I am open to some questions because I was supposed to stop at 11. I I had some problems in sharing the slides. I hope everybody could see the slides.
Yes, sir. No, not a problem, sir.
Okay, okay. Initially, I had problem in changing the slides.
Okay,
And
not
I
a
had
problem.
to slide through them rather than going to the next slide. Thank you. Any
Thank you. Thank
questions
you.
from people?
Any questions from the audience poll, please? Any questions from the audience poll? Okay, sir. Thank you. I think no questions is there. So
Yeah,
I'll hand over the session to the Dr. Chandrappa, sir.
yeah, yeah. Thank you, thank you, thank you.
Thank you very much, sir, for giving a very good session, and it was so informative. And
Hope it is next generation. Hope it is next generation.
yes, sir, yes, sir. Sir, I request our the chief coordinator of the conference, Dr. Jayati Kumari Madam, to present a moment as a token of respect virtually to the Murali sir. On behalf of Murali sir, just I received
Yes.
with permission, I received the moment, sir.
Yeah. Thank you. Thank you. Thank you very much. Thank you so much.
Thank you, sir. Thank you very much.
Thank you.
So kind of sir with us today, and with all
Yeah,
the busy schedule,
thank you so
we
much.
spent,
Hope it was useful. Hope it was useful.
transfer very important information on time sensing networks. So because this is the new technology where it has to be adapted for the next generation. Thank you, sir. Thank you very much, sir.
Thank you. Thank you very much. Thank you. Thank you so much.
Students, the sessions will be start from exactly 11:15. Be prepared with your the respective tracks. Thank you all.
ಎಷ್ಟೊತ್ತಿಗೆ ರಾಜೇಶ್